Welcome. We're so glad you're here with us for today's Harper Lecture. The Harper Lecture series began in 1979 with Hannah Holborn Gray speaking in San Francisco. As the need for critical thought remains apparent in all areas of life, we proudly continue this signature program to bring you stimulating conversations and fresh ideas. Our UChicago community is a global one, and we are thrilled that technology can help us stay connected to one another. As you enjoy today's lecture, please note the following items. Your camera and video will be off. However, we encourage you to ask questions. Please use the Q&A box at the bottom of your screen to ask a question at any time during the talk. Closed captions are available by clicking the box at the bottom of your screen. Click Show Subtitles to enable this feature. If you're having trouble with audio or video, please try shutting down programs in the background, or you can dial in from your phone. Thank you once more for joining us. We couldn't do this without you. Hello, everyone, and welcome. Welcome to today's Harper Lecture, The Unseen Universe, How It Impacts the World We See, with Professor Marcela Carrena. I'm Andrea Hodgman, Associate Director for Intellectual Engagement and Travel and the Program Manager for the Harper Lecture Series. I'm so pleased to welcome you to today's event. On behalf of everyone at the UChicago Alumni Office, thank you for joining us. Please allow me to introduce our moderator. Angela Alinto is Dean of the Physical Sciences Division and the Albert A. Michelson Distinguished Service Professor of Astronomy and Astrophysics. She works on astroparticle physics and cosmology, and she has made important contributions to the physics of quark stars, inflationary theory, cosmic magnetic fields, and astroparticle physics. She currently leads NASA's suborbital and space missions to discover the origins of the highest energy cosmic rays and neutrinos. This past spring, she was elected to both the American Academy of Arts and Sciences and the National Academy of Sciences. Professor Carrena, Dean Alinto, thank you both for joining us. Dean Alinto, I'll hand things over to you.
Thank you so much, Andrea. It's a wonderful pleasure to be here tonight with you. I wish we were in 3 dimensions, but we'll take the 2-dimensional version of our Harper Lectures. And it is a great pleasure because tonight we have a wonderful treat. We are going to listen to Marcela Carrena. She is a leader in particle physics. She's a distinguished scientist and the head of the theory division at Fermilab, the Fermi National Accelerator Laboratory, for those who don't know what Fermilab means. She's also professor of physics at the University of Chicago, where she is a member of both the Enrico Fermi Institute and the Calvi Institute for Cosmological Physics. Her research explores the possible connections between the Higgs boson, the dark matter of the universe, and the origin of matter in the early universe. She has been a leader in exploring radical new concepts such as supersymmetry and warped extra dimensions, and how these ideas can be tested in experiments. Professor Carrena works closely with physicists at the largest particle accelerator on Earth, the Large Hadron Collider at CERN. And in particular with scientists at Fermilab and UChicago, creating and implementing strategies for discovery. Recently, she is exploring ideas at the boundary between particle physics and quantum information to tackle problems of quantum theory and the early universe. I have known Marcela for several decades. We're not going to be precise about that. I am thrilled to be introducing her today, as I mentioned, even though in 2D we cannot have a wine afterwards, but we'll get a rain check for that. We used to meet often at Aspen Center for Physics and Fermilab, where I was a postdoc at one point, and then she came as a scientist to lead the theory group. And she has been a role model to me, even though she's younger than me. When we both started our careers, the number of women were so small that we had to use each other as role models because we didn't have too many other options. So I was very lucky to have encountered such a brilliant physicist leading a wonderfully challenging field, also coming from Latin America. As you might know, I'm Brazilian and she's from Argentina. And as long as we don't discuss soccer, or futebol as I call it, we can be best friends. And just to prove that point, both of us risk our lives by bungee jumping off a balloon together. So that takes a lot of courage, and so does to be a leader in her field. So I'm very pleased to have Marcela tell us a little bit about her recent work. So thank you, Marcela, the floor is yours.
Thank you, Angela. Thank you for this very nice introduction. You also have been my role model, so it's reciprocal. And it's always a real pleasure to share time with you, discussing physics or in bungee jumping, testing firsthand the force of gravity. Let me start on today's lecture, the unseen universe and how it impacts the world we see. So preparing this lecture made me think of watching the Flying Dutchman, Wagner's opera that you may have seen, in Berlin with my 5-year-old son quite a few years ago. It was probably quite a stretch to bring him there, but he was fascinated. And to be more precise, let me just use my pointer here. Okay, so to be more precise, we were sitting just here at the theater, and we had a bird's eye view of the stage. So in the Berlin Opera House production I saw some years ago, the ship suddenly came out from the backstage towards the public, flying. It was very impressive. What we saw was amazing, but what we didn't see is what really fired our imagination much more. So today, we are going to go through a journey to explore the invisible world, which makes possible the magic of what we see in our everyday life and in the whole universe. So I will start by talking about 3 pieces of the invisible world. The first one is an invisible field of energy. It allows all we see, stars, planets, people, opera houses, to exist. The second is dark matter. It shapes the fabric of our universe. It's what holds our own Milky Way together, and it distorts the images of distant galaxies, as I will tell you a bit later. And I would say that in the analogy of the theater, dark matter is all what we cannot see at all, but we know it must be there. It's like the cables of a stage that hold the ship and make it appear to be flying in the tempestuous sea. The last topic I will discuss, and which is entangled with the other 2, are virtual particles. They exist for an instant and disappear the next. But as we shall see in this lecture, they can change the world we observe in very important ways. And again, in the analogy of the theater, it makes me think of the musical chords vibrating for an instant and then being silenced. They are also ephemeral, but profoundly touch our senses in a very lasting way. So let's start with the invisible Higgs field, the invisible Higgs energy field. It is a field of energy that permeates all space. The one example that we are quite familiar with is the Earth magnetic field. It has a source, the Earth, and a direction determined by the Earth spinning around itself. It is invisible, but we can tell it's there because it pulls on the needle of the compass to point towards the north. The invisible Higgs energy field, which I hope you can see very clearly here, is produced by itself. That's already quite strange. And it affects it has a big effect on us, but it's not really pulling in any particular direction. However, we know it is there because it makes particles massive. So particles as the ones that make you and me and the stars shining in the sky in the night. So if you could suddenly turn off this Higgs field, then all the particles will become massless again, and the universe as we know it today will not exist. Okay, so that's great, but you may ask yourselves, how do we know that the invisible Higgs field I'm talking about is at all real? This invisible energy field was proposed by Mr. Higgs here in this picture 57 years ago. At the Nobel Prize ceremony in 2013, where this picture is coming from, he said to me and to my good friend here, CERN Director General Fabiola Gianotti, the following: my first paper was rejected because it was not relevant for real physics. It has very beautiful math in it, though, he added. And indeed, you can see here these equations, and these equations may mean nothing to you, correct? But just as musical notation looks undecipherable for the uninitiated, they both can be interpreted to reveal a harmony in nature. Anyways, Mr. Higgs said that in his second version of the paper, the one that was finally published, he added that we could prove the existence of the invisible energy field by looking to its associated particle, the Higgs boson, a new particle we have not seen yet, but yet at that moment of the paper. So now he said, let's go and look for the Higgs boson. And my friend Fabiola here and her colleagues did indeed look for and discover the Higgs boson at the CERN Hadron Collider. And this happened, so this was first presented in July 4th of 2012. So it made a big splash in the whole world, as you can see, and it brought tears to Mr. Higgs' eyes. Okay, so I already told you that it took half a century after the Higgs idea to really discover the Higgs. And we need to build the Large Hadron Collider, the most complex, most expensive, and largest machine ever built by mankind. So the Large Hadron Collider is here in the city of Geneva in Switzerland. And I could say that you know that your experiment is really big. These are the 4 cameras that we have to look at what happens inside the Hadron Collider. So you know that your experiment is really big when it is big compared with an international airport. So now I would like to show you a picture, an animation actually, of an actual collision when the Higgs was, I need to change this, yeah. So when the Higgs is created and transformed into particles that we can see in our very specialized cameras that we call detectors. So let me switch on this movie that has no sound, so I will walk you through this. So we go inside the Large Hadron Collider in a tunnel that is 300 feet underground. We have the proton moving inside the ring at very, very fast, almost at the speed of light. They cross the French-Swiss border. They don't need any passport. And we see here the protons are with particles themselves that are the quarks and the gluons wiggling, and they accelerate, and a beam of protons go in one direction and the other beam in the other. And when they arrive to our detector, they collide. Kaboom! This is the Atlas detector. When they collide, they produce a lot of debris. But among this debris, they actually produce the Higgs boson. The Higgs boson, why we know is there, is because we see immediately that it transformed into other 4 particles that we can see with our detectors. And as you see in this picture, 2 of them are electrons, and I will go again to my laser point, sorry. So we see here, you have 2 electrons and 2 other particles that penetrate much more the detectors and are these blue tracks, and they are called muons. And we will come to talk about muons much later on in the lecture. So here we are recreating conditions of the early universe when it was about 10th of a billionth of a second old. So a real baby. Okay, so I already told you what made possible the Higgs boson in the sense of building the Large Hadron Collider, but what really made possible the discovery of the Higgs boson? And the answer are virtual particles. All the fundamental particles of nature that we know of can behave as virtual particles as a result of the uncertainty principle that was first thought of by physicist Werner Heisenberg. The uncertainty principle is really an element of quantum theory that expresses the wave-like nature of particles. And what it means as a result of the uncertainty principle is that for a very short time, a very large uncertainty in the energy of a particle can allow it to spring into existence from nothing. What this means that empty space, quantum empty space, is full of virtual particles that exist for an instant, but have real effects on our world. So this mind-blowing feature, at least it is mind-blowing to me, of the quantum world plays a crucial role in particle physics experiments, as we will discuss more later now. So the thing that is important is how virtual particles can make a Higgs boson. So if you look at how we discover the Higgs boson, you will see that virtual particles are at the core of it. So here we will smash two protons, and the protons are made, as you see here, from gluons, that are these wigglings, and from quarks of two different types. But when we collide the protons, what we really collide are the two of the particles that are inside them. You would have thought that to make the Higgs boson, we need to collide two heavy particles, since the heavy particles are the ones that talk the most to the Higgs. Indeed, a particle mass is one-to-one related to the strength with which it connects to the Higgs. But here what we do is we collide gluons. Gluons have no mass, so don't talk directly to the Higgs. So the gluons collide in the quantum vacuum in the Large Hadron Collider, and they create virtual top quarks. And top quarks, as you see here, the gluons collide and create, these are top quarks in reality. And the top quarks that exist, so they are virtual particles, and they exist for a little while, and they are able to create the Higgs boson. And the top quarks are indeed the most massive particles that we know. So without this trick of the virtual particles, the Higgs boson discovery in 2012 would have not happened. So we got the Higgs boson. With that, Mr. Higgs' theory explains how particles get mass via the invisible field energy that is the Higgs field. Now we are using the Hadron Collider to understand in detail how our new friend, the Higgs boson, really behaves. Moving to our next challenge of the invisible world, I will try to tell you a bit how we understand what it is that matter made of, or what we don't. So we know that matter exists because galactic and cosmological observations show that there is much more matter in the universe than what we can see. But we do not have a clue what that matter is made of or why it is there. So let's start looking at the first evidence for dark matter through its interactions with visible matter in the Milky Way. In the 1970s, Vera Rubin and her colleagues started to measure how fast stars are moving in galaxies like the Milky Way as they orbit around the center of the galaxy. From standard gravity, we would expect that the stars that are farther away from the center of the galaxy and farther away from our sun would be moving more slowly in their orbits. And this is exactly what I draw here with this red curve, that is assuming that the only matter is the one we see. But this is not what Vera Rubin found. She found that the most distant stars in our galaxy, so she found this white curve, that the most distant stars in our galaxy are moving about as fast as our sun in their orbits. The laws of gravity, as we know them, would imply that the stars moving with this velocity as this distance from the center of the galaxy will just fly away. The explanation is that the visible matter that we see here is actually embedded in a much larger crowd of invisible dark matter. In fact, we know today that about 90% of the total mass of the Milky Way is in dark matter, not in planets, not in stars, not in the nebula. Nowadays, we have many other sources of evidence for the existence of dark matter. And let me just walk you through one of them that is called gravitational lensing. As Einstein told us long ago, space-time is distorted by the gravitational effect of matter. That makes the light that is coming from distant objects to move in curved lines, as you can see here, before reaching Earth. So gravitational lensing is what distorts the images that we see from distant galaxies by bending the light. And the effect is that we see these distorted images in our telescopes. And here is a beautiful picture that is only an analogy, but shows how a curved surface could disturb the images, in this case, of the Chicago skyline. So nowadays, we can use computers to make a map of where all the mass must be in order to create these distortions that we see here. And we use machine learning and sophisticated tools. So as shown here, in this scale, a galaxy is just a point in this space. And the spikes that you see, that you see here are the galaxies. But also you see this mountain of something here, and this something here is dark matter. So what do we know really about dark matter? Unfortunately, we know very little. As I showed you before, we know that it couples gravitationally to us. We also know that it's the most abundant form of matter. If we consider matter alone, it ends up making 85% of all the matter in the universe. We also know that it needs to be something different from all the particles we know in different ways, but in one way that is obvious is that it cannot be interacting through electromagnetically in the way other particles do, at least not the majority of it. So dark matter could be other particles we don't know, could be some very heavy, massive objects, or can be very light and behave more like a wave. And also dark matter could be a mixture of all different components. Also very interesting is to think that dark matter can be a part of an invisible dark world with new dark forces. And we, in today's understanding, we think about these ideas by connecting this dark world to our world through some portal. And in fact, one of the possibilities of being a portal is the Higgs boson itself. So, of course, we would like to detect dark matter in the laboratory. Indeed, we know it is everywhere. So we are trying to make our detectors to catch it and study and see what it is. Obviously, even better is if you can try to make the dark matter, to create dark matter at the particle accelerator, like the Large Hadron Collider, in a similar way as we did with the Higgs field. However, it's hard to design an experiment that is going to look for something that we do not know what it is. It's quite challenging. So our strategy as theorists is to make educated guesses of what the dark matter can be. And here are some people at the University of Chicago and Fermilab, not all of them, just a handful, big handful, who spend their time thinking about dark matter. And here in the center is Michael Turner and Rocky Kolb, who have been pioneers in thinking about explanations of dark matter. In fact, I think that they were thinking about that even almost before Angela and I were born. So Mike was the wizard, as you see here, who coined the very nice name WIMPs, Weakly Interactive Massive Particles. And this has been for decades one of the most promising ideas to explain dark matter. Okay, as a theorist, we can try to connect the system of dark matter to other mysteries of particle physics. There are other things we don't understand. One obvious one, of course, is how to explain that there is more matter than antimatter in the universe, or think about unification of forces, and so on. So these ideas, as you see here, leads to a lot of very interesting names, like the WIMPs I mentioned, axions, even nuggets, that I'm not sure exactly what they are, but they're one type of the many that we have there. And so we can imagine many different extensions of our world. Some of them has enlarged harmony in nature. Some of them may have additional dimensions of space. And most of them are involving the existence of new forces. Okay, so meanwhile, with ultrasensitive detectors and telescopes, experimentalists are pursuing three basic approaches to try to pin dark matter that I'm trying to show here. One is above ground, so is to look the evidence out in our galaxy of dark matter, either colliding with the matter we know or annihilating or decaying into it. And here is the AMS detector at the International Space Station. So what we are trying to do here, for example, is to look at an amount of positrons, like charged cosmic rays, that is not what will fit what we think within our standard theory. As I mentioned before, we would love to create dark matter at the Large Hadron Collider. We know in the Large Hadron Collider, we know how we put the energy in the collision. And if we look carefully, and it looks like we lost some energy once after colliding particles, we made the particles that we know how to account for, then the missing energy could be going into dark matter particles that fly away from the collision. And this is something that we are pursuing quite energetically. And the third one is to build ultra-sensitive detectors that might catch the dark matter that is out there streaming in from space. And of course, in this case, so this is underground, this is deep underground, because we need to protect ourselves to avoid the cosmic rays that are also streaming in from space and would make it very difficult to detect the dark matter. And I would like to mention that University of Chicago, as well as Fermilab, but in the University of Chicago, there is strong leadership in all these areas. And we are pursuing also novel possibilities with quantum technologies. So dark matter exists, and I hope I convince in this short presentation that we are leaving no stone unturned until we know what it is made of. So let's take a closer look now, moving to our third topic, to virtual particles and what they may bring along. In fact, they could help us create dark matter in the laboratory. And some virtual particles that we do not know that exist could also point us to the right theory to explain dark matter. So the next part of the lecture will ask the question, are there virtual particles that we don't know of? And what can we learn from them? So let's move to last April 7. I was thrilled to watch my Fermilab colleague, Chris Polly, unveil the results of the muon G-2 experiment for an audience of thousands of people. This experiment is actually especially designed to be sensitive to the effects of virtual particles. So let me just, here. So while I was doing that, suddenly I was remembering a time many years ago when I was traveling. Let me just put this smaller. So when I was traveling in a high-speed train, away from CERN and moving to my next job in Germany, looking through the window at the scenes flashing by. Each was just, a few flickering frames, gone in the blink of an eye, but enough for my imagination to fill up the story. At that time, I had just finished analyzing the flickering effects of virtual particles on a very special property of the muons, the cousins of the electrons, the same property that is under scrutiny now at the Fermilab experiment. So today again, I'm trying to discover the story behind muon G-2. Okay, so the first question should be, what are muons? As I told you, muons are cousins of the electron. However, they are heavier. They are 200 times heavier than an electron, and they are unstable. If they were at rest, they would live for 2 millionths of a second or a microsecond. So as we see in this picture, there are showers of high energetic particles which occur when energetic cosmic rays strike the top of the Earth's atmosphere. And if we look at this cartoon here, we see that there are cosmic rays that hit the atmosphere, and they go into secondary cosmic rays, and finally they produce muons. I don't know, I mean, in the picture, as you see, they put a Concorde airplane and I think a helium balloon to give us the idea of which is the altitude at which this is happening. I remind you, a Concorde airplane can reach up to 60,000 feet, and a balloon more than twice of that. So the muons can hit you and me and the Earth. In fact, more than 10,000 muons are passing through our bodies every minute. And muons are an amazing source, cosmic rays are an amazing source of muons. And if you have questions about cosmic rays, I will tell you to please ask Dean Angela, who is a world expert in cosmic rays. But today we want to talk about the Fermilab muon G-2 experiment and how the muons are produced there under controlled conditions, very different from what we do from what cosmic rays do when they produce the muons. So we have an accelerator at Fermilab, and it produces protons, and the protons smash a target, and finally they produce the muons. And the G-2 experiment sent these muons into this magnetized loop that you see here. Please pay attention to the beautiful blue color, come up back at the end of the top. So this magnetized loop where they circle around in a vacuum until they decay. Before moving further, you may want to know, where did we get this ring from? This is a 50-foot long ring of magnets. And in fact, we got it 10 years ago for free from Brookhaven Lab in New York, where it was there because it was being used by a muon G-2 experiment that took place 20 years ago. So this 50-ton apparatus came from Long Island to Chicago through the Atlantic Ocean, through the Mississippi River, as you see here, and through highways. And it arrived to Fermilab in a beautiful stormy day. So now let's try to go more into the experiment. So the Fermilab experiment really measures the wobbling muons. As I mentioned before, muons are cousins of the electron. They have the same type of electric charge and a property called spin that electrons also have. And this spin reacts to magnets. So the spin points in a given direction, like the needle in a compass. And this is these yellow arrows. I will go back to my pointer. So this is these yellow arrows that you see here. So this is a diagram of the muons. So as you see, as I told you, these are the protons. They hit the target. The target made some other particles called pions, and these pions finally make the muons that are going into this magnetized ring. So the magnetic field makes from one side the electrically charged muons orbit around the ring. And this is what we see here in the pink arrows at very high speeds close to the speed of light. But it also causes the spin to precess smoothly like a gyroscope when the muons go around the ring. So that's what happens with these yellow arrows. But in fact, it also causes a small wobble in the precession of the spin. And that's why these yellow arrows are not aligned with the pink ones. And this small wobble in the precession of the muon, we put it in our calculations proportional to a factor that we call G-2. So your natural question would be now, what causes the wobbling? And the right answer is the vacuum factor. So if muons were alone in the experiment, their spin will not wobble and G will be equal to 2. So this will be what happens. However, as we very well know, quantum empty space is never really empty. So virtual particles appear and disappear in the experiment, and they interact with the muons, changing the behavior of their spin precession. And this is what we see in this other picture, where G is larger than 2. Okay, so this is just the effect of the vacuum factor. And however, theories can compute the muon wobbling that we expect from all the particles we know in the universe. And in fact, we do it. Here, for example, one of the known particles is the photon. And so the muon is going into a virtual photon and a virtual muon for an instant that is too short for us to measure, and then becomes again the usual muon. We can measure this fluctuation, but we can measure what it does to the behavior of the muon. So now we are ready to compare the wobble we measure with the one that we predict with our theoretical calculations. So now let's go back to April 7th. So here is a picture of my colleague, Chris Polly, who is presenting the first result of the muon G-2 experiment at Fermilab. And as you see, what happened really, or as you may have heard, better said, the wobble the experiment measured was bigger, significantly bigger than the one that we had predicted. This caused quite a big surprise, and you can see here in the front page of the New York Times, it says a particle's tiny wobble could upend the known laws of physics. It got a lot of attention from the whole world. Mike Bloomberg said the most extraordinary event of the year. And I would say even Luke Skywalker acknowledged that the force seems to be with us. So, okay, the Fermilab experiment measures significant more wobbling than predicted. The discrepancy is such that we are close to the very rigorous threshold we require to claim a discovery, the same as we did with the Higgs boson. So now, if this holds, then these results seem to challenge our understanding of modern physics. And of course, here are all the theories working, many of the theories who are working very hard to understand how to explain the Fermilab results. It has to be something new because we already know that we were able to account for all the known effects of the particles we know in nature. But that's not so unexpected, since we already know that something is missing, as I told you before. What is that matter? And also, we don't know precisely the properties of our new friend, the Higgs boson, and they are actually still mysterious to us, and we are studying them at the Large Hadron Collider. So theories are proposing many new scenarios with new particles and new forces, and those scenarios are very strongly constrained, but all the data that we have taken from many sources in many decades. Whatever is the case, some scenarios could connect to the nature of, could tell us that the muons are connecting to a different world, And in any way, the muons are telling us that something that has implications well beyond the muons themselves. So what we are doing here is the muon G-2 results are just one piece of the puzzle. And at the moment, we are trying to decipher the whole puzzle from this one piece. Muons may be interacting with virtual particles that we don't know of. That could be necessary if we want to have an explanation to this discrepancy. And these virtual particles that we don't know of could be cousins of the Higgs boson, or could be exotic particles that may connect with dark matter and dark forces. So here, I love this picture, is Mr. Higgs and his cousins, some of his cousins maybe. And here is Harvard professor Cora Dworkin, a UChicago alumna, who is looking for evidence of dark forces in the cosmos. So we are searching for these new ingredients that might be there in experiments like the Large Hadron Collider and in other type of experiments around the world. And we also think that this might show up in, oh God, sorry, this might show up in other places like the structure of the cosmos. So what's next? And I'm about to conclude. So I could say that we are trying very hard to understand this enigma. And so more data from the Fermilab muon G-2 experiment is about to come. So we already have 10 times more data that is going to be analyzed in the next couple of years. And meanwhile, theories are rechecking the theory predictions. We are really have been refining theoretical predictions for decades, but some of the details are really quite hard to compute. And we have developed new mathematical tools and very sophisticated approaches. But what we are trying to do now is we are going to use some of the most powerful computers available. And you see it here in the screen, the Summit IBM cluster that is in Oak Ridge lab and will be used in the next years to refine the theoretical calculations. And similar powerful computers are being used by other theoretical teams in Europe. So still so much to discover. I want to share, to finish this picture, I was at the muon G-2 experiment a few weeks ago. And as you see there is a white cover over the beautiful blue ring that you saw before. So I asked my experimental colleague, why? He said, well, you know, Marcela, we work super hard to control all aspects of the experiment with the most advanced technologies we have. And we need to control very precisely its temperature. So we are using the world's oldest technology for that, a blanket. So many new results will come soon, so please stay tuned. And I hope you have enjoyed this presentation about the wonders of the unseen world, and I am available for questions. Thank you.
Yay. I wish everybody could clap, but
That's good. I see some.
At least you got some reaction here. This was lovely. I was busy answering some questions, but there are many more to be answered. So thank you, Marcela, if you can take some questions from us. Folks sent some questions ahead of time and others are happening right now in the Q&A. And I think there's still 9 to be answered. So we'll try to get to some of these. Maybe not all, depends on the time, obviously. But thank you for submitting your questions and you can keep them coming and we'll see how fast we can get through. So first question. If there are cousins of the Higgs boson, I like the cousins in the mirror there of Peter Higgs, why haven't we found them already?
Okay, that's an excellent question, Angela. Thank you for posing it to me. So in principle, we should be able to make cousins of the Higgs boson at the Large Hadron Collider. But the point is, it was already very hard to make the Higgs boson there. And if these cousins are much heavier, than the Higgs boson, then they will be produced in much smaller numbers, and it would be much easier to that they remain hidden in all the debris that we saw in that collision. So right now, Fermilab and University of Chicago are part of a bigger project worldwide, US and Europe and other areas in the world. But in the US, there is about $1 billion project to improve the capabilities of the LHC, so that if the cousins of the Higgs bosons are there, we hope to find them. And the last thing I want to add to this, because it's very dear to my heart, is that the cousins of the Higgs boson are also extremely interesting because they appear in all theories where we want to explain the matter-antimatter asymmetry in our universe as generated by the Higgs field itself. So if we want to say that this matter-antimatter asymmetry occurred when the Higgs turned on 1/10 of a billionth of a second after the Big Bang, then for sure we need to have additional cousins of the Higgs boson around.
That is so exciting. We're looking forward to populating that family of Higgs. Is there any connection between the Higgs or any other of your topics to the fifth force? That seems to be something being discussed at CERN these days.
Yes, well, that's a very natural question to ask. So, in fact, there have been some new results from one of the main four experiments at CERN. It's called LHC-B. And there, what we see is that they show there is some unusual behavior of the muons. So related to the second part of the talk, there we were showing some unusual behavior of the muons in the muon G-2. In the LHC-B experiment, what happens is that they produce some unstable composite heavy particles that have something that is called beauty quarks inside them. And when they decay, they seem to decay differently to electrons than to muons. They decay less to muons than to electrons. And for all what we know, we would expect that the transformation of these particles into muons and electrons would be of the same order. So both the LHC-B and the muon G-2 experiment indicate a departure of the behavior of the muon with respect to the known physics. Okay, and it is reasonable to wonder where both results are just different, flickering frames of the same story. And of course, theorists have been, and myself included, have been working on trying to put, the pieces of the puzzle together very much. It turns out that it is possible to put both pieces of the puzzle together, but not in the most simple theories you can think of. You can do that with quite involved scenarios, because what happens is that the G-2, in order to explain G-2 and to explain LHC-B, the strength of the new forces that you will have to explain both together, and especially to explain G-2, are a bit too strong, and they are constrained or excluded by other experiments. So it is possible, it's not very easy.
So I'll add to one question that's on the Q&A by Franklin Felber. So the answer to what laws of nature did G-2 experiment unpend? I think the answer is we don't know yet. Which law of nature got unpended? So people like Marcela are trying to find the answer, but I think it's, to be continued, I would say. Yes. So let's move to a little bit of cosmic rays. I can't resist. The unseen cosmic, this is a question that came up too. Love to know how unseen cosmic rays and other phenomena can have impacted or guided evolution of ecosystems and species on Earth. So some connections with biology here.
Yeah, this is of course a very interesting and exciting question. And I'm not an expert, but I will try to say a few thoughts here. In fact, there is a nice, the answer is, I think, yes, cosmic rays and muons have indeed impacted and guided evolution of ecosystems and species on Earth. There is actually a nice article that I wish I would understand better. It's published in Astrophysical Journal Letters, and it's by my colleague Roger Blandford, that claims that cosmic rays may have a role in the handedness of life. Means that DNA is right-handed, while the associated amino acids are left-handed. And so I think I would like to have to go back and read it more carefully to give a better answer, but it seems that at least some smart people are thinking about that and finding that there is something to be said about how it impacts our life here. I think that so I think life on Earth is quite protected from galactic cosmic rays. Maybe Angela, you can add there, because only the second radiation can really, cosmic rays can reach out, and some of that is already protected because the muons decay. So as I told you, there are a lot of muons arriving to us as we speak, but I think altogether on the Earth surface, we are reasonably protected from cosmic rays, although I know this number because Fermilab makes us learn it, that an average American receives about 620 millirem per year, and half of those are coming from environment and cosmic rays. So yes, there is an impact, but I think you and I were still here, so I think it's okay.
Yeah, but it probably did change species slowly through very long time scales. But it is an issue also for astronauts or people in the future who want to go visit Mars. That will be quite a trip. You're going to be having a hard time surviving the cosmic ray trip. But anyway, that's something to be figured out by space agencies. All right, so let's move into a more interesting in the sort of global sense. It's not local to the solar system, but you mentioned that the Higgs will be, if we could turn it off, it would be hard to do it everywhere, but let's imagine that possibility. Then all of a sudden particles will become massless, and the universe would not exist. So as we know it. So what exactly is that? What do you mean by that kind of?
Yeah, there are quite a few things that can go really wrong if particles become massless. So let me just mention a couple. So the first one is that if you look at equations of quantum mechanics for atomic systems, it comes that the radius of an atom increases with the mass. So increases with the mass of the electron decreasing. So it's inversion proportional, correct? So what this means is that as the electron becomes massless and its velocity approach the speed of light, the radius of the atom becomes infinite. And what this implies is that the electron is not any longer bound to the proton, and therefore there is no atom, okay? So in other words, we know that chemistry depend on atoms, but electrons will fly out at the speed of light and atoms will not exist. So that's quite basic. There are other things that will be in quite a bit of trouble. So we know that protons and neutrons will still remain massive because they're massive by the binding energy of strong interactions. But the difference in mass between protons and neutrons are actually due to their constituents, the quarks that are inside the protons and the neutrons. And if the Higgs would be turned off, then the mass of the quarks, the up and down quarks that are inside the proton and the neutrons, will also be turned off or will become zero, okay? And then, for example, the proton would be expected to be heavier than the neutron. It is the other way around in nature. Due to the electromagnetic effects. And this will change basically nuclear chemistry in a very radical way. And among other things, the proton will decay, that we have not seen it yet. So that's another area. And the last area that I think is not less important is that we know that what we call the force carriers or the particles that basically are in charge of the weak force, okay? So what happens is that if these particles that are also not Higgs bosons, but W and Z bosons, so are the particles that are basically responsible for the weak interactions. And these weak interactions, which for massive particles are of short range, will become of very long range. And this will affect in a very significant way the proton fusion in stars like our sun. So this will be essential in changing the process of energy generation in our stars. So the sun will not be shining the way it does. Let me put it that way. So we hope the Higgs doesn't turn off.
Yeah, I would imagine a lot of things moving very fast, which would not be good for creating any structures, including humans.
Exactly.
Okay, so there were lots of questions about dark matter and how do we know for certainty that there is dark matter? Could there be a modification of gravity, for example?
Yes, so I hope I kind of show you in this experiment a little bit how dark matter should be there. Okay, I gave two examples. I talk about dark matter at the galactic level that is inferred by the rotation of velocity, the rotation velocity of stars in a galaxy. And I mentioned Vera Rubin. There was also a previous rougher estimate by Mr. Zwicky in 1930s that was talking about the rotational velocity of galaxies in cluster of galaxies. And in fact, he was the one that pinned the name Dunkel Materie, which is dark matter. I also talk about gravitational lensing and how is the fact that there is more matter than what we see, that we see these distortive images of distant galaxies. But then there are other things, and I think you partly mentioned already that, Angela, is that dark matter plays a crucial role in structure formation, in how the structure of the galaxies, and which are really with observable matter, we will not be able to form, let me say, the potential world that is formed by dark matter to make the structure of our universe. Okay, so and the manner in which the structure grows depends on the amount and also on the type of dark matter. We are trying to study how dark matter works. Is it self-interacting? Is it not? And for that, we need to understand structure formation. Of course, there is also dark matter is a necessary explanation when we study the temperature fluctuations in the cosmic microwave background radiation. And I think most recently there are these beautiful pictures of Chandra X-ray Observatory, where they have these pictures of the bullet cluster, where we see the evidence of two merging galaxy clusters, and we can see in the center the hot gas of visible matter that is slowed down by the drag of the other cluster. And then we see the collisionless dark matter passing by, and we can see that through the gravitational lensing effect. So it's clear we don't know for certain, 100% certain, the existence of dark matter. I will go to your issue about modified gravity in a second, but I think the evidence is quite overwhelming. And yes, there have been ideas, many ideas, different ideas, where you can think that you modify gravities at larger distances so that you can account for these rotational velocities of stars, for example, and that can be done. But to put all the many pieces that I'm telling you, all the many pieces together, it's very hard to do it unless we think that dark matter exists.
Excellent. I think we're close to ending here, but maybe a quick last question, which is, are there other invisible particles that we know of that you didn't talk about? So known unknowns, and then we'll wrap up.
Thank you. Thank you. This is a great final question. Yes, they are, and they are called neutrinos. And in fact, Fermilab have a very strong ongoing program and planned program to understand better neutrinos. They are the most abundant particles in nature, and they are very elusive. because they interact with us very little. When the first person that thought about the existence of these particles was Wolfgang Pauli. And that was because looking at the neutron decaying, the neutron goes into a proton, an electron, and something else. And that something else is this neutrino in order to preserve energy. So today we know very well that the neutrinos are real. They play a very important role in the evolution of the universe and also in this process of nuclear fusion that leads to the star's energy generation. And the neutrinos, for a long time, they were believed to have zero mass. In fact, in our more simple model of particle physics, we were not putting any mass to the neutrinos. But now, today, we know that the neutrinos do have mass because we have seen some very special property of the neutrino that is called neutrino oscillations. And this is a very basic idea. So we have the neutrinos that are being produced. For example, as I told you, a neutron goes into a proton, an electron, and something that is an electron neutrino. But once this electron neutrino has been produced and starts moving on its own, suddenly it turns into, with some probability, into a muon neutrino. So it's like you bought an ice cream that is chocolate ice cream, and a block later, you realize that you have vanilla ice cream, and you don't know how this happened. Okay,
that's a good one.
So this, depends if you like vanilla and chocolate. That's all good. So the simple way is that there is this mass of the neutrinos that kind of mixes up one electron neutrino with one muon neutrino. And we know really that there are three types of neutrinos. So electrons, muons, and some other a little heavier ones that are called taus. So we want to understand the neutrinos can tell us a lot, as I said, about the evolution of the universe. They also, there are some theories that try to explain the matter-antimatter asymmetry through the existence of some heavier species, cousins of these neutrinos. We know they exist. And so there are many experiments, including those at Fermilab, that are trying very hard to see if there are more cousins of the neutrinos that could shed light on things that we want to explain.
Wonderful. Thank you. Thank you. This was incredible.
Thank you, Professor Carena. Thank you, Dean Alinto. We'll see you next time.